We're going to keep working on dynamic programming for the next 3 or 4 days, then a little bit on greedy, and then a little bit on the relationship between greedy strategy and dynamic programming. As I told you last time, dynamic programming is kind of an alternative to recursion. If you think of recursion as divide and conquer or top-down, dynamic programming is the same idea, but the implementation is bottom-up. It's a divide and conquer strategy whose sub-problems overlap and you get multiple calls to them. So you try to do it from the bottom up. Now sometimes this helps and sometimes it doesn't. It helps when the total number of subproblems all together end up being polynomial. If the number of subproblems altogether is exponential, then it doesn't mean squat that you can go ahead and generate them all, because when you're all done, you've still done exponential work. So it works when the number of subproblems total is polynomial, but then when you actually use the recursive structure, you end up calling them multiple times. Then you do it from the bottom up, and that's what dynamic programming is really all about. And it's used in all sorts of different situations. So we started yesterday with some simple examples like Fibonacci and binomial coefficients. We'll review binomial coefficients very briefly at the beginning of today to make sure everybody gets it. And then, here, let's pass those snow cones over to Joe here. All right, we're going to review the binomial coefficients briefly, and then we're going to move on to other areas, to shortest path, etc. But before I do, I want to give you a preview of what will be done in recitation. I don't know if we'll get to it at the end of this week, because I'd like him to go over the exam at some point this week. But it'll either be right before you go off on vacation for the weekend or when you come right back on Monday. One of the recitations in dynamic programming will talk about 2 different problems that I will not have time to talk about in class, because there's so many examples. And recitation will be used to not really present new ideas, but just to present new examples of the same ideas. And there are 2 famous examples. One comes right from the book, and one is from a problem that's not in the book, but it's really kind of cool. So the one that Mark will do that's from the book is a problem called longest common subsequence. And it's a simple idea. Imagine that you have like long sequences of letters. And it goes on, whatever, 1,000 different letters. And then you have another sequence of letters. And you want to be able to slide these over each other to match up the longest common subsequence that they have. So in this case, I think the longest common subsequence might be just 3. It might be BAC. There's also CAB. There's a couple that are 3 long. So where do you think this comes up?
String matching?
Well, it can be used in string matching, but string matching we either want to match exact or we want to match kind of a close approximation. And here we just want the longest. So it might be useful, but I think most of the time it's either you want an approximation or an exact. But where would you want to make these kind of matches? DNA. Yeah, this comes from a DNA problem where you've got these long, and instead of the A, B's, and C's, they're who knows what, I forgot already, guanine and GTAC or something, right? So they have to match up, and you want to get the longest strands, and you want to match them up. And you need algorithms like this. There's another place where it actually comes up, more obscure, but I saw a cool TV show on it a few months ago, and it reminded me of this algorithm. People, when they find these old wooden artifacts that have been buried in the mud, try to age them, try to figure out when they were built for historical and archaeological reasons. And the way they do it is they take the wood and they look at the rings in the wood. And presumably the wood was cut off in a geographical area near where that thing was built. And they have, it's amazing, libraries of ring patterns for particular trees in particular areas for 800 years at a shot, from big, big trees that they've cut down and they've kept track of. And the ring patterns change depending on whether there was a drought or lots of water that year or what was happening. So what they try to do is take these chunks of wood from the stuff they find and match it up with the longest amount of patterns that match in the rings to get a good sense of what year this thing was actually built. So there's a lot of patterns that might recur, and the shorter ones are less sure that it was really built in that time, because maybe if you can find a longer one, you'd match it up further back or closer to where you are. And they really do this stuff, and they have computer programs that go and try to find these matches. And some of the tricky parts is that sometimes, I mean, you need historians here to get a sense of whether this thing was actually built in this area. And sometimes you can get really misled because what you actually find turns out to have been built in some place 500 miles away, and nobody ever thought that ships were being, say, sailed from that distance in that time, so nobody thought of checking trees that were in that area. So, I mean, there's just interesting questions that come up, but you do need that algorithm kind of at the bottom of it.
How do you translate ring patterns in trees into computer language?
So you try to digitize the rings, the thickness of the ring, the darkness of the ring, and the width of the ring. And you just give it some kind of a bit pattern. And then you try to get the longest bits that match up. So it's really kind of neat. So I was just telling them, Mark, that you're going to talk about this longest common subsequence problem sometime in the future.
Probably today.
Probably today. There you go. So if you have any old pieces of wood down in your basement, bring them in and we can match them up in the rings. They do find ships like this buried in the mud, and they do try to figure out where they were from and figure out a little more about history.
How far back do they have ring patterns?
I think pretty far back. I think 1,000 years back. Maybe more.
Who's been doing that?
I mean, there are old trees, and then there's old things that were built out of older trees. So you kind of piece match it. It's a detective puzzle. I don't know really how far back it goes. It's conceivable it goes back, that their records go back even more than 2,000 years. I'm not sure. I should really, you know.
They're saying that all trees have the same ring pattern from the same area?
The same kind of tree in the same area will have the same kind of ring pattern. Yeah. It depends. It depends primarily on how much water and what the heat was and things like that. So they grow a lot in a good year and they grow a little bit in a small year. Yeah. Yeah, if you're a tree, you got no place to hide. Yeah. All right, the other problem that Mark's going to talk about, and this is really cool, and I wish I would talk about it, but I'm letting Mark do it because it's just so much fun. It's a cool problem that if you're given, everybody knows how to make change, you know, once you get past 5th or 6th grade. And, you know, somebody gives you $1.50, says $1.52, and you have to go ahead and come up with $1.52 out of, say, 50-cent pieces, quarters, dimes, nickels, and pennies. So the problem is to do it with the fewest number of coins, right? Because you don't want a big bulge hanging in your pocket, whatever. Fewest number of coins to make your change. So it turns out that the best way to do that, or a way that does it accurately for our coin system, for the 50, 25, 10, 5, 1 system, is just to do it greedy. Take as many 50s as you can, and when you can't take any more, take as many quarters as you can, and when you can't take any more, take as many dimes, then nickels, then pennies, and you get the smallest number of coins that way. That's a greedy strategy. You're doing the local thing, and it works out for the global picture. But it turns out that it isn't too hard to come up with a set of denominations of coins for which that doesn't work. Not 1, 5, 10, 25, 50. It does work for that set. But you can come up with a different set of coins, and then the greedy strategy won't work. It'll actually give you more coins than you actually need. There is a dynamic programming strategy that works for both cases, whether the greedy strategy works or not. And that's an interesting trade-off, whether you go with a greedy strategy or a dynamic programming strategy, because sometimes there's a choice. And that's a cool problem where there's a choice. And Mark mentioned to me, I didn't know this before, but he mentioned that the related problem, if I give you a number of coins with denominations, and I ask you the question, will the greedy strategy work or not, that problem is NP complete. Is that true? Is that what you... Yeah. So that's an interesting point. So if I give you, whatever, 50 coins with different denominations, and I say, will the greedy strategy work here? That's a hard question to know. It doesn't mean you can't come up with an example where it won't work, but you just can't solve it in general. Okay, so that's all intro. Binomial coefficients came up a lot in discrete math. And you write them like this. It stands for how many ways there are of choosing m things out of n things. And we had a combinatorial theorem that we talked about in discrete math. This is a little bit of review, but I want to make sure everybody remembers. How many ways are there to choose m things from n things? Well, let's say one of these m things is special. and I set it aside, then either I'm going to have that special thing in my group or I won't have that special thing in my group. Now let's say I include that special item in my group. I'm definitely including it. Then the number of ways for me to choose the rest of the items is, I only have n minus 1 items left, and I'm only going to choose m minus 1 things, because I've already chosen the special item. The other possibility is that I don't choose the special item. If I specifically do not choose the special item, then I still have n things to choose from. Sorry, did I do that right?
N minus 1, choose m.
N minus 1 things to choose from because I'm not choosing the special item, but I still have to choose m different things because I haven't chosen any yet. And that's where the recursive relationship comes from. The number of ways to choose m from n is the number of ways to do m minus 1 from n minus 1 plus the number of ways of doing m from n minus 1. That's a recursive relationship, and if you calculate it recursively, you get an unbelievable number of duplications. So in the notes, there's new lecture notes up, and you can get them, but in the notes, I list this out, and I'll just review it quickly. For example, if you try 6 choose 3, then, and you do the recursion all the way down, then here's a list of things. It happens to do 3 choose 2 3 times. It does 3 choose 1 3 times. It does 1 choose 1 6 times. It does 1 choose 0 6 times. It does 2 choose 1 5 times. If you go through the recursion and you get all the subproblems, this is an example of the duplications that you get all the way at the bottom. Some things only get duplicated once, but some things, especially toward the bottom, get duplicated many, many times. Okay, and the example is written out in details. The key thing is that you wouldn't do this recursively because of this duplication. You would try not to. The way to see this duplication actually happening is to write up this relationship in a table. And here's what the table looks like. It's called Pascal's triangle. Today I'll write it like this, which makes it look more like a two-dimensional array. This is row 0, row 1, row 2, row 3, row 4, and row 5. And this is column 1, column 2, column 3. So this would be 2 choose, did I do it right? No. 0, 1, 2, sorry. This would be 2 choose 0 is 1, 2 choose 1 is 2, 2 choose 2 is 1. You can look up n choose m by looking here for n and here for m, and just find it in the table. And the relationship is that each n choose m relates to the one that is above it and to the left, that's this one, and to the one that's just directly above it, that's this one, and you add them together. And now you can see why you get duplicates, because as you start with something down here and you work your way up, it goes up and to the left, but then the one next to it's going to go up and to the left, and you get these overlapping things, and the overlap grows and grows and grows. And it grows very, very badly. We reviewed yesterday just how bad it would be if you make a recurrence equation to see the time of this recursion. It's very bad. Let's consider n and m together, the sum of them, to be the size of the input. Then the time this takes, if we call that k, then it relies on a problem that's size 2 less, and another size problem that's 1 less. It looks just like Fibonacci numbers. That's the time it takes to solve this binomial coefficient problem recursively. It's too slow. It's exponential. By the way, without going through all the incredible details of solving recurrence equations from discrete math, how do you get a ballpark figure on this really quick? Here's how you do it. This recurrence equation is somewhere in between these two, which are much easier to solve. Okay? The top one is a little bit bigger than this, and the bottom one is a little bit smaller than this. Okay, there I've put 2 tk minus 1s. Here I put 2 tk minus 2s instead of one of each. Now these are much easier to solve. These you can solve just by substituting. You can almost do it in your head. Every time you subtract 1, in this case, you multiply by 2. So when you subtract down n minus 1 times to get to the base case, you've multiplied by 2 n minus 1 times. So this ends up being about order 2 to the n minus 1. or order 2 to the n. There's some details, but more or less. And this one ends up being what? Who can guess? Every time you multiply by 2, you're cutting it down by 2. So when are you down to the 1 case? When you've cut it down by 2, n over 2 times. So it's 2 to the n over 2. And 2 to the n over 2 is the same as 2 to the 1/2 to the n. That means the square root of 2. So this is about, square root of 2 is about 1.4 to the n. So it's somewhere in between 1.4 to the n and 2 to the n, more or less. And the actual number is some ugly thing with this, well, or beautiful thing, depending on how you look at it, with the golden mean ratio. Square root of 5 plus 1 over 2 times 1 over the square root of 5, which is in between 1.4 and 2. But it's definitely exponential, and it's some relatively high number. It's not, 1 plus teeny epsilon. It's close to 2. So it's bad.
Theta is approximately 1.6. The golden mean.
1.6. Okay. Yeah, but there's also this other constant square root of 5 factor, so it might be a little bit different. But it's something in between there, and it might be a little higher than 1.6 when you're all done.
The theta would be 1.6.
The theta would be 1.6, yeah. Okay. Questions about this so far? So the main thing of dynamic programming is there's usually going to be a table associated with it. There's usually going to be a polynomial number of solutions. If you want to get n choose m, and the recursive way is bad, let's just start from the top and fill in this table with a loop. Okay, that's an intro programming problem. I equals 1 to n, j equals 1 to m. Use this relationship to fill it in. And by the time you're done filling in the first n rows, you'll get here pretty soon. And it's going to take, at most time, n times m. At most the size of this rectangle. It's actually n times m divided by 2, more or less. So it's pretty fast. Nowhere near the horrible exponential time you get there.
Is that faster than just calculating the force? It's not
Faster than just using factorials.
Well, it depends what you count as your operation. If you count every addition as an operation, then the factorials here have to still do m operations. Anyway, you're getting down to a low level of how you count operations. But another way to do it is just actually do the factorials. But if you unravel the factorials into the loops, that they actually require, the number of multiplications or the number of additions, it can take similar time. I've actually done experiments with this, not for binomial coefficients, but for the 7-ring puzzle, where you get a similar kind of recurrence relation, but you actually calculate it better from the bottom up. So if you do that, then to calculate the exact number of steps that it takes to solve the n-ring puzzle, if you do it by just calculating the factorial formula, or if you do it by running this loop, it's almost indistinguishable for fairly large numbers. But of course, doing the recursion takes forever, relatively speaking. Okay. Questions so far? Another thing you should notice is that in doing it the dynamic programming way, we have decided to calculate all the subproblems because we don't know exactly which ones we'll really need. We do know we have to get up to here. And in the recursive way, we only calculate certain ones on the way back because we know exactly which ones we'll need. So we trade off calculating every single one exactly once for calculating specifically the ones we need too many times. And that's also very typical of dynamic programming. The last thing that's typical of dynamic programming versus recursion is recursion goes with stacks, and dynamic programming, if it goes with anything, goes with a queue. All right? Now, in these examples, you don't see a queue. And the reason you don't is because it's very easy to order these subproblems. You can do it with a loop. You go row by row. And most of the time, the examples you're going to see, that's the case. But sometimes, it's too difficult to order it. There's no natural way. And the only way to order the subproblems is to start with a base subproblem, and see which ones it generates, and throw them in a queue, and do those next, and see which ones those generate, and throw them in a queue, and do those next. So kind of doing a breadth-first search from the bottom up. That's the more general way of doing dynamic programming. It's as if I didn't know I could do this row by row, I'd start with this one and figure out which two it generated, and it would generate this row, and that would generate the next row, and that would generate the next row, and that's done in a queue, that breadth-first style. And you'll see one example of that all the way at the end of the next few days. So keep in mind, if there's a connection between data structures and these two styles, then queues go with dynamic programming, stacks go with recursion. Okay, other questions about this example? That's all I'm going to do. There's a lot more to remember about binomial coefficients and about Pascal's triangle, but they don't relate to what we're doing. Just this is enough to get the connection to dynamic programming. So I'm going to switch gears. This is going to take a little bit of time. I certainly will finish it today, but I don't know how much more time I'll have to work on it. But I want to make sure everybody gets it. So I'm going to go through it little by little because it's a really super example of dynamic programming, and there's more than one variation of this. So let's talk about it in general. We've already talked about shortest path algorithms. We've talked about them when you have positive edges. We've talked about them when you have no cycles. We've talked about them when you have negative edges but no negative weight cycles. And we had 3 different strategies. Shortest distance first strategy, that's Dijkstra. We had topological scanning strategy, that's when there's no cycles. And we had breadth first strategy, that's equivalent to the Bellman-Ford algorithm. And every one of those had a different time complexity, and they were up on the board here a few minutes ago. So the topological scanning one, who remembers? How long does that take? I'll let you think. Dijkstra and breadth first search scanning, equivalent to Bellman-Ford. How many steps does this take, topological scanning? Right, you have to topologically sort the graph, and then you just go through it one node at a time, and you never scan anything more than once. When you never scan anything more than once in a shortest path algorithm, that takes basically E time plus N, because you might have to go through things that are not there, but approximately E time. And the only issue is whether you have any other data structures that need maintaining. So in topological scan, you don't, but in Dijkstra, you do, because every time you take a node off your heap, you have to reheap the thing. So it ends up being E log n. There's another version of Dijkstra that doesn't use a heap and uses the 2-dimensional array, and that ends up being n squared. And we talked about there's a trade-off. Sometimes this one's better, sometimes this one's better, depending on how bushy the graph is. 2 ways to do Dijkstra's algorithm. The breadth first search scanning algorithm, the way I showed you is better engineering-wise. The way the book does it is just perhaps easier to describe. But altogether, both of them have worst case n times e. All right, that's shortest path review. You can certainly use any of these to find the shortest path from a given node to all the other nodes in the graph. Right? That's what it's used for. And I mentioned that as outside of engineering points of view, nobody knows any better way of going from a single node to a single node. You might as well get everything else for free, because nobody knows any better way to take advantage of that. So we don't talk about single to single. But we do talk about getting the shortest path from every node to every other node. To do it from one node to every other node results in a distance array and results in a shortest path tree with that node as the root. If we wanted to do it from every node to every other node, one way to do it is just to do either one of these, depending on which graph you have, n different times. Once for each of the different nodes as the root. And your output would be n different distance arrays, and your output would be n different shortest path trees. Okay? Now, that means instead of having just a distance array that has one parameter, you'd have a distance array that has 2 parameters. There'd be an I and a j. The I would be the root that you've been searching from, and the j would be the normal distance to that node from this node. So now your one-dimensional output has become a 2-dimensional output. Your array of distances becomes a 2-dimensional array. Your parent array is the same. Pij means what's the parent of j in the shortest path tree that's rooted at I. In the shortest path tree where you're going forward from I and looking to all the other nodes, what's the parent of j? So if you want to find the shortest path from I to j, you do Pij. That would give you some other node. And if that node's called k, then you do Pik. That would give you some other node. Call that m. Then you do Pim. And sooner or later, you would get nil. And that would give you the list of nodes that go all the way back from j to I. So just single-dimensional things have become 2-dimensional things. And the complexities of all these algorithms just multiply by n. This becomes ne, this becomes n cubed, this becomes ne log n, this becomes n squared e. And that's all there is to that. The thing is, Once we're doing a different problem, there might be a better way than just to iterate what we know already. And that's what we're going to talk about for the rest of the day. We're going to talk about a dynamic programming approach, blow all this stuff away, forget that you ever knew how to do it, and solve it from scratch with a different approach. Now, this is an interesting idea because it's useful, and it's an idea that most people don't have in their repertoire of solving things. Sometimes it's easier to solve a problem if you make it harder. Right? Now, that's a funny way to say it, but I really mean exactly that. Let's say that you spent 3 years and you came up with neither this, nor this, nor this idea. You could not figure out the idea of scanning. It didn't occur to you. You had no idea how to do a shortest path problem. But you were an expert at dynamic programming and recursion, and you were really good at that kind of stuff, even though this kind of stuff just seemed out of the league. And then you sat down and you said, well, I can't figure out how to do a shortest path from a single spot to any other single spot because I'm confused about it. But if I make the problem harder and wonder about how to get the shortest paths from every place to every place, suddenly a recursive structure shows up, and I can solve that problem. Even though, at first glance, that problem seems harder than this, because it can be thought of as just n iterations of this. So adding more to your plate sometimes gives you a structure that breaks the problem down where you didn't have it broken down before. Everybody knows take a big problem, break it into pieces, and solve the pieces. But not everybody always thinks of take the simpler problem, I have no idea what to do, and I'm going to add it and make it harder, and now there's more structure. But it's an idea that works a lot in computer science and in math, both algorithmically and also in proofs. All right, so we're going to come up with a method that solves this problem using dynamic programming and doesn't use any of these. Okay. What's a good way to motivate this method? When we did the Bellman-Ford algorithm, and I proved to you that it actually ends, it finishes, it doesn't go on forever, what was the key idea there? How did we know that it was going to end? How did we know that we weren't going to keep putting things back on the queue forever? What happens there? Every time you put a new level on the queue, you're guaranteed that the distance values are correct for all paths that have as many edges as that level number. So at the second level, you're guaranteed that the distances are right for all paths that have 2 edges in them. When you do it again, you're guaranteed that the distances are right for all paths that have 3 edges in them. And the longest path in a graph has n minus 1 edges in it, without going over an edge, which we're not allowed to do, n minus 1 edges. Therefore, all you have to do is do it n minus 1 times, and you're guaranteed that those distances after that will never change. That's why Bellman-Ford has the loop on the outside from 1 to n minus 1, and it says it's finished, because it knows if it kept doing it anymore, that nothing would change. And there's a theorem that says this, that after every level, you get the right numbers with 1 extra edge in your picture. The reason I'm reminding you of that is because the dynamic programming algorithm that we're going to start with leverages that idea of adding in 1 extra edge to the length of the path every time. It leverages that idea to get a recursive formulation for shortest paths. Here's where we're headed. The first version we're going to do is going to run in order n to the 4th. The next version we're going to do, which is a minor improvement of this, cuts it down to n cubed log n. And then finally, we're going to get to what Mark mentioned briefly yesterday, what's sometimes called the Floyd-Warshall algorithm. And that's a better recursive formulation, a different idea altogether. And that automatically starts out at n cubed, and that's the best you can do there. So these are more for getting warmed up, and that's kind of the cool one. If you compare these complexities to n times all the others, you can see which ones are better, which ones are worse. But I should tell you that these algorithms, every one of them, work in all the most general cases. They don't need positive edges. They don't need acyclic graphs. As long as there's no negative weight cycles, these will all work. So you should compare these to the n squared e that we get by doing n iterations of Bellman-Ford, because that's what they're really working with. Okay? If you have restrictions on your graph, you probably wouldn't use this. You'd probably go use n iterations of some of your faster algorithms, because that would be quicker than n cubed. Okay, questions so far? Good. Okay, so with this motivation, I'm going to write down a symbol, and this is very common in dynamic programming. We define the thing that we want to compute, and then we try to come up with a recursive relationship for it. Let me tell you what the symbol means, and then we'll come up with a recursive relationship for it. We're going to have this big two-dimensional array, or, well, it's 3 dimensions, I suppose, but dxyk, or a function. It takes x and y, 2 things in your graph, and it calculates the shortest distance between x and y. K is the number of edges that are in the path. So this gives you the shortest distance between x and y when there are at most this many edges in the path. Everyone understand what dxyk is? I'll write this down. Shortest path, x to y, with at most k edges in the path. If we could calculate this, then how could we find the answer to our question? What the shortest paths are overall between any 2 vertices? What would it be? dxy what? What would this number be for k? As long as it's n minus 1, then we've got our answer, because there can't be more than n minus 1 edges in any path. dxyn minus 1, dxyn, dxyn plus 1, dxyn plus 2, they will all be the same. Once you get to n minus 1, this thing has become stable. So if we figure out a recursive relationship here, all we got to do is start it at n minus 1 and work our way down to the base case and figure out what those answers really are. I got to warn you that this is not the best way to do it. As I said, it gives you n to the 4th, and if you're clever, n cubed log n. But Floyd-Warshall is a little more clever. And Floyd-Warshall does not use this recursive scheme or this definition. And that's the biggest challenge in a dynamic programming problem, is to choose this well. You have to decide what it is you want to compute. And depending on what you decide and how you describe it, it'll either have a nice recursive structure or a not so nice recursive structure. And most of the time, I'm just going to be telling you, oh, this works. And it's tricky when you're coming up with a problem where you don't know what works. You're going to have to use your own ingenuity and practice a little. Part of the reason I'm doing this example is to show you one that seems natural but isn't quite as good as one that is less natural. Floyd-Warshall is not as natural as this one is, to think of right off the bat. Okay, questions? Good? Clear so far? Good, all right. Questions for you? What is dxy1? Describe it to me. What does it mean?
Shortest single edge path between x and y.
Shortest path between x and y that use at most 1 edge.
Infinite unless x and y are adjacent.
It's going to be infinity, but if x and y are adjacent, it's going to be what? If x and y are not connected, then this is infinity. There's no 1 edge path between them. But if they are connected, then it's equal to the edge. So just remind you of something. How do you describe a graph to begin with? Right. You can describe it with a 2-dimensional array. We've been describing it with adjacency lists, but let's do it with a matrix. Okay? In honor of the movie, yes. We'll get Keanu Reeves as a guest speaker. Yeah.
I'd rather see Shai doing it kung fu.
Okay, let's turn this into a 3x3 matrix. A, B, C, A, B, C. What does it look like? The AA is a what?
0.
Right, the diagonals are always 0. Okay, there are no connections there, unless there's loops. We didn't have loops in our graph. No loops. If there's a loop, you'd put a value in. A to B is 2, A to C is 4. B to A is...
C is not.
Oh, so there's no A to C, sorry. A to C is infinity. B to A is infinity. B to C is 4. C to A is infinity. C to B is infinity. That's it. That's what the graph looks like. This is actually the input to any algorithm that you'll use if you use the two-dimensional version rather than the adjacency list. In the adjacency list, it would just have a link with 2 on it. Here it would have a link with, with 4 on it and a C. It wouldn't include the infinities and the zeros. But if you have a two-dimensional array, you put in everything. This picture of the input to the graph is exactly the same as dxy1. It means the same thing. So if you just want to figure out dxy1, just look at your input and say, I'm done. But that's not so useful. You got to get dxy2, you got to get dxy3, dxy4, etc. All right, but you should realize at least that at the lowest bottom level, the base case, it looks exactly like this two-dimensional array. That's why in this algorithm, we don't use adjacency lists. That's why in this algorithm, we use the two-dimensional array, because conveniently for us, our base case is exactly the same as the input. And if we took it in adjacency list, the first thing we do is read it into a two-dimensional array and think of that as our base case. So why don't we just start with a standard way of putting the input in, which is the same as what we need. And that's why we use 2D arrays instead of adjacency lists here. Good? You all get to the point? You ready? All right. Here's the harder part. Let's get a recursive relationship for this. Let's try to get dxyk in terms of smaller cases. Well, the x and y are not going to get smaller, but the k can get smaller. The k is going to go down. We're going to get dxyk in terms of dxyk minus 1s. Let's see if we can write this out. Let's say you know the shortest path between every point x and y that uses k minus 1 edges. And you're trying to figure out the shortest distance between every point x, y that uses 1 extra edge. How can you build these numbers out of these numbers? That's the hardest part of a dynamic programming solution. And it's just recursion. You have to think about it. How do you build these out of these? All right. Here's one way. You're starting from x. You're trying to get to y. You know you're allowed to use, say, 7 edges. You happen to know that the shortest way to get from x to y using 6 edges is a particular number. You know the shortest distance between x and anything else using 6 edges is a particular number. So here's one thing to try. I'm trying to get from x to y. I'm allowed to use 7 edges. I know the fastest way to get between every pair with 6 edges. I want to figure out what the fastest way to get to here is in 7 edges. By the way, I know the fastest way to get to here in 6 edges too. I'm adding an extra edge. I want to know, does it help? Well, here's what we can do. Let's go all the way to y and stop right before we get to y. Call that m. Go to some node that connects to y and stop there. Now you know the fastest way to get from x to m with 6 edges, because we did that already. Let's take that number, add it to whatever the weight is on this my edge, and see if that's better than the way that we previously knew to get from x to y using 6 edges. In other words, adding this edge, do we get a better way? Adding that extra edge in, do we figure out a faster path? Let's say the best way to get from x to y before was 20, and the best way to get from x to m before was 15, and this weight is 3. Now we know we can get from x to y in 18 by using that extra edge. That extra edge helps us. Everybody get that idea? Not yet. Let me say it again.
Was there already an additional edge in there between, if m is a node before y?
Mm-hmm.
There was already an my node or edge, right? No.
The edge is always there in the graph. The edge is always there in the graph.
Whether you're using it, but you weren't already using it.
Well,
Seems like
let me give you an example that'll make it really clear. 1, 2, 1, 2, 3, 4, 5, 6. 1, 2, 3. I got to get 6 inside. 1, 2, 3, 4, 5, 6. There, 6 edges on the way to y. Let's say that path altogether is 20. Okay? The best way to get from x to y using 6 edges is 20. Let's say the path from here to here is also 6 edges. And it adds up to 15.
From there to where?
From x to m, which is right before y.
Oh,
Say this is the whole graph.
M isn't a node on your previous path?
It's just any node in the graph that happens to connect to y.
Okay.
So let's say at this point, what do I know? I know that the best way to get from x to y using 6 edges is 20. Because if I try to go this way, which will be faster if I could take that last edge, if I can only use 6 edges and I go this way, it's infinity. Because I can't get to y in 6 edges this way. I can only get up to m. So if I add in that extra edge, I find out that I can get from here to here in 6 edges with 15. I knew that before. Add in the extra edge, which gives you 3 more. That gives me 18. So now I know I can get from x to y in 7 edges with 18. And that's better than I could do with 6 edges. That's our recursive idea. We're going to go right up to where we're trying to get to, see if adding the extra edge in gives us paths that we didn't have before. Shorter paths that we didn't have before. I still some confused looks, and I'm going to write down some details, but I want to answer questions first. So, yeah,
You have to
question.
pick m not only that is one edge away from y, but that's 6 edges away from x?
Not necessarily. Let's say m was 8 edges away from x, and there was no way to get there in 6 edges. Then the current distance x to m would be infinity. And we would check whether infinity plus 3 was better than 20. And we'd say it isn't. So we don't have to check directly whether it's 6 edges or less. We'll have that implicit in our distances. If there's no way to really get to m in 6 edges, then the distance there will be infinity, and it'll never be better than what we had before with just 6 edges from x to y.
But it can't be less than 6. Like, what if it was only 4?
That's okay, because our distances are the shortest paths from x to y with at most k edges in the path.
Except at this point, it would not be only 4, because if it were only 4 and could get to y in just one step,
Then we would have known that there was one with 5 that goes to y. That's true. That's true. That's true.
We don't know that there isn't one with 5. We just know that it's not shorter than the one with 6.
That's true. That's right. But in this particular example, it would be shorter, so we would have already changed the x to y. Other questions? Peter, do you have a question? Yeah. No? Okay. Other questions? Well, let's write this out in a formal way. Let's take our inspiration away and write down what we just wrote before. We're going to take our x as a starting point, go up to some other node, somewhere in the middle, m, and use k minus 1 edges to get there, and ask ourselves, what's the best way to get to m? And then we'll move from that edge m over to the edge, the node y, and we'll call that the weight of my, and we'll calculate this. We'll go to every single node in the graph. We'll check to see what its best distance is with k minus 1 edges. We'll add in how much it costs to take that last edge over to y, and we'll see if this is better than what we currently have. What would happen if m didn't connect to y? Then the weight of my would be infinity, and then this would never be better than what we have. So we don't have to specifically say that m has to connect to y. And we don't have to specifically say that m is, exactly 6 edges or 5 edges. All these things will work just as they're written. Teresa, you have a question? You're thinking?
I wish you could give me a real-life circumstance of why you would sort of know.
We're going to do an example soon. We'll do an actual example, and you'll see.
Is this incorporating your thought earlier about you making the problem worse and then you're coming back?
Yes, it is.
Okay, well, then I haven't.
This is hard. This is hard stuff. It's hard to get the idea first. Yeah, Tony? What?
Your weight function?
That's just this.
It's just a look up DMY1.
The weight function is this array. This is weight, yeah. Yeah, it's just a lookup in the two-dimensional array.
You currently have
Yeah,
functions.
Mike?
There may be some sort of implementation detail,
Mhm.
but these functions are all this point to this point. And there is some sort of greater thing that's running this through all of these points.
Yeah, we haven't written any loops yet to do it, and we will get there. We're going to do that very soon. We're going to do it right now, in fact, and then I'm going to do an example. All right, so look at this again. We're going to calculate this for some middle point m. And we're going to see whether it's better than what we have. And then which one are we going to actually use for dxyk? We're going to use the one that gives us the smallest. So I'm going to write the minimum of all this stuff over all m.
That and
Right, so now let me be
possibilities.
I'll do my Kreskin mind read. Chris was thinking, oh, but it's also got to be better than what we started with before, the dxyk minus 1. It's got to be better than what we had before, right? So maybe I should have written this and then also add in dxyk minus 1, because it might be that you don't get anything better by adding the extra edge. But this actually includes that, because m can actually be it can be x or y, so it includes that as a possibility technically. So technically I don't have to write that in again. It's already in there. Okay?
Maybe I'm jumping in at the wrong time. I'm going to wait.
All right. Wait, here we go. We're going to actually write a little loop here and then do an example. Maybe it's best to see an example really early, but if I do one too soon, I'm not sure you'll get it, and I think you will get it at some point. I want you to get this main idea first, and I want you to see a little bit more code. Michael's feeling a little uncomfortable about not seeing exactly what I'm going to do with this, and he's right. I mean, we really should write it up a little more carefully. Maybe you were feeling comfortable, but no. Let's make this work. Okay, here's how it's going to work. We're going to be very specific now. Instead of writing things dxyk, I don't like 3 parameters in the parentheses. We're going to cut it down to 2, and what we're going to do is this. Notice that once we calculate dxyk, do you care about dxyk minus 1 anymore? No, blow it away. dxyk is going to help us get dxyk plus 1, and dxyk plus 1 will help us get dxyk plus 2. So instead of keeping all the different versions of these, we're just going to throw the last one out when we get the new one. Okay? So that's a technical detail that we should realize. So instead of having dxyk, we're just going to have dxy. And at the beginning, dxy is going to be what we called before dxy1, the first one. What should that be the same as? What's dxy1? What's our initialization? The weight. So it looks like this, where the weight is given to you as your 2-dimensional input array for your graph. So dxy equals wxy, that's the initialization, and this is for all x and y. It's a little loop. X equal 1 to n, y equal 1 to n, copy it over. Okay? We are now going to make the next version of capital D be dxy2. And the next version of capital D will be dxy3, and when we're all done, capital D will be dxy n minus 1, and it'll have the absolute correct distances in there. Good so far? Yeah, okay, so now we're going to have a big loop. K starts at 2, since we've already done 1. And we're going to go all the way up to, how far? Yeah, n minus 1. In my notes I did n just to make sure. But I'll go with n minus 1. That's fine. Now what does it look like? Basically what we want to do is implement this minimum calculation. We want to do it not just for a particular xy, but for every xy. Okay? So, there's going to be a loop inside here. For x is 1 to n. For y, 1 to n. A big double loop. For every single one of those pairs. Joe? Okay? All right. So now we got to do something inside. Inside is this. Right? How are we going to write that? Here's what we're going to do. We're going to need kind of a temporary 2-dimensional array to hold the new one. And when we're all done, we'll copy it back into the old one. Because the new one kind of depends on the old one. And I don't want to write over it while I'm doing the calculation. I want to leave this one pristine, copy it into a new one, and then copy it back when we're done. Okay, so this new place I'm copying it over to will be, we'll call it D prime. And when we're all done doing this copying out here, before I go back, right here I'll copy it back. dxy equals d prime xy. That's a loop for all xy. Okay, so we're going to calculate a new d prime based on the old d, and when we're done we'll copy it back and we'll do it all again. Okay? this is a technical thing. I could maybe write it back into the array that I'm working in, but I didn't want to deal with any potential conflicts, so I just used a different one. All right, so what's d prime xy going to be? It's based on this. Here's what it looks like. Look at dxm and dmy. Sorry, not dmy. wmy. Look at dxm and wmy. Look at the best way to get from x to m that we knew last time. Look at the edge, if there is one, from m to y, and see if this number is better than what we used to have. So we're going to calculate this minimum over all m.
Where's the m coming
So
from?
you need another loop with it.
You need another loop, m equals 1 to n. And in this loop, you're going to have a little thing that calculates the minimum you've seen so far, and when you're all done, you'll put that minimum back in here. I'll leave out a little of the detail of the programming, but some loop here that calculates the minimum of these as m moves from 1 to n, gets you the best one, stores it in here when you're all done, move to the next pair of xy. Do it again, move to the next pair xy, do it again. When you're all done doing all the pairs xy, copy all your nice new values, namely your dxy next value of k, copy it back into the one you started with, and do it all again. That's what the code looks like. Yeah, Joe, question.
Should that be d prime xm?
You mean in here?
Yeah.
No, this should be the old one. The one, dxm represents dxm k minus 1. And dxyk is what we're calling d prime here. So we got this fresh new area, and we're using the old area with all the values that we already calculated. We're doing the calculation and filling in the fresh area. So this area is just clean stuff, and when we're all done, we copy it over back into the old area. So you get it?
Yeah.
Okay.
M are just the nodes adjacent to Y, right? So
No, they're every single node.
They're every single node, but
It's true that we only have to consider the ones adjacent to y, but it's going to take just as much time to find those than it will take to just run through all of them. Because we have a two-dimensional array here. How do we find the ones that are adjacent to y? You've got to look through the whole row and see which ones are non-zero or infinity. Just that if statement, you might as well do this. Right?
okay.
Right? So you're right, but we don't have any way of leveraging that. We can't do it any faster, since we're already using this two-dimensional array structure. So we might as well just look at all of them and have the infinities never switch.
Well, won't you get y, the weight of y to y,
You will.
and that'll give you 0?
You will. You will.
That's not fun.
No, it's not. In fact, it's important. Right. Let's consider that. Neil brought up a really good point. You will consider m equal to y. What does that say? It says, is the best way to get from x to y using 6 edges, and then staying at y and doing nothing, better than anything that you can get with adding an extra edge. It's saying, is the best thing we had before better than anything we get by adding an edge? And that's important because otherwise we might actually replace an old thing with a worse thing. That's what makes sure we never ever go worse, because we always consider what we had before, which means going all the way up to where we were before and then not adding the edge. That's what I said before, where I anticipated what Chris was thinking before he cut his question off, that you really do have to check the one you started with, and that's done because we let m vary and it actually hits y. So that's a programming technicality, but it's cleaner to write it this way. Yes, Svi, and then Donna.
Aren't those two situations kind of symmetrical? If you're going over all the nodes, could you change the W to a D? Like if D was on the left, shouldn't it work on the right side as well?
Okay, so when I was little and used to visit the FBI in Washington, D.C., there's a relevance here, but remember what you asked, and I'll get back to it. And they used to have the shooting thing at the end. It was the thing all the kids waited for. You know, here's the lab, here's this, and they go, show us the shooting. And then finally they'd show the shooting, and the first kid who would raise his hand and say, can I have, you know, the picture of the man with the holes in his head and his heart, you know, they'd say, oh yes, you know, any questions? And of course there was never any question except that first kid who could yell, give me the sheet. So anyway, and then you get the sheet. I don't know what they do nowadays, but Tzvi gets his name up here. since he's the first one who thought of this idea. Zvi's idea of changing this W to a D, and then, oh, there's a bunch of details involved, blah, blah, blah. But that's really the improved version, and we'll talk about that later. So hold your question, wait till later, and you get to have your name up for a while. And everybody gets to learn how to pronounce it. Donna, have a question?
Yeah, I just have a...
I'll put your name up too, it's all right.
No, that's all right. When you set D equal to D prime, do you do that before you increment K? Each time?
You mean here?
Yeah, I'm just trying to figure out.
Yes,
Okay,
yes.
It's not the end of the whole formula.
No, it's here. It's yes. I got, that's, yeah. The brackets bracket a loop. The M loop, the double XY loop, the K loop. Good question. All right. Other questions? Before we do an example, before we talk about it anymore, before we talk about Zvi's suggested improvement, how long does this take? It's not so hard. How long does it take? Right, because I said so. Let's see why. It's got 4 loops. They're all inside each other. There's no clever thing here, where you're only taking something off once and you look at it twice. I mean, these are all nested inside each other. M goes 1 to n, x goes 1 to n, y goes 1 to n, k goes 2 to n minus 1. It's n times n times n times n. It's n to the 4th. No two ways about it. No way to clean it up. Okay. I think what we need to do now is look at an example, and then we'll switch over to the n cubed log n version, and then we'll blow this whole idea off and say, you know what? This is not a good way to write it up. There's a more clever way. This is the first recursive way you might think of, but it's not the best. And we'll get a whole factor of n better. We'll get it down to n cubed. I want you to concentrate. So I am going to do an example that is directly in your book. You do not have to copy this. It's there. Just watch and do the example together with me. Think about how to construct it, not how to copy it over. So it's a relatively short example. It's got a little pentagon, and there's not too many edges in it. But it'll be a good attempt at really understanding what's going on, because you're going to be forced to go through the details. Whoop. Oh, I hate this. There we go. All right. Ugh. All right. This edge is 8. This edge is 7. This edge is 2. Right? It's hard. I don't know how people draw these and always get it perfect, but I never do. So here's W and here's D1, and you tell me what it is. I get to choose. Don't raise your hand. If you don't know, just smile at me and I'll pretend I didn't call on you. Smart guy. Did I say we have to label the vertex? All right. We got A, B, C, D, E that go this way. A, B, C, D, E. A, B, C, D, E. Let's fill this in. How'd you know I was going to call on you? AA is 0. Good. All right. Diagonals first. All right. You got a bunch of zeros in the diagonal. What about AB? What about the idea of me calling on people? I got it written down. Everybody know how to do this? All right, let me write it down then. Jeez. Okay, to infinity and beyond, yeah. Infinity, 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 6. All right, that's what D1 looks like. It's the same as the weights. It's the same as the input. It's the same as that graph picture up there. Assuming I didn't make a mistake. Gador, did I make a mistake?
Why is B to D1?
I think you're missing an edge from each D.
Because I didn't write it in. Yeah, now it's 1. It should be there. Okay.
Can you have a loop to it itself the weight?
Yes.
Sorry.
Yes. But only in the twilight zone. You can, but it doesn't come up in most applications. All right, let's calculate D2 together. When we calculate D2, we're going to write it over here. And I want you to notice something really neat about doing this. And I'll give you it, well, I'll let you discover it as we do it. Let's calculate D2. We got to do it for a lot of values. So maybe after a few and everybody gets the idea, we'll quit. But let's start at the very, very beginning. We'll do D2 of A. What do we actually do? It's a lot of work, actually. We do D of A with the weight of A. That's 0 plus 0. That's not better than 0. D of AB plus the weight of BA. That's 0. And D of AA is 0, and D of BA is, and W of BA is infinity. We're doing MA and then MB, and then M equals C. So that's infinity. That's not better than 0. So now we do D of A, C, plus W of CA, which happens to be D of CA here, and that's also infinity. Well, you can all see that happens to be only, well, what's going to happen when you go through the whole thing?
Nothing's going to be better than 0.
Nothing's going to be better than 0. This is one edge. If you make two edges, there's no way to get back to A and do any better than 0. Unless there was the negative cycle that went from A back to itself, which there isn't. Right. So now let's do A to B. Is there a way to get from A to B faster in two edges than we can in a single edge? Let's see. A to B. So we'll try AA, WAB. That's the same. We'll try AB, weight of BB. That's the same. We'll try AC, weight of CB. AC, weight of CB. That's 12. That's worse than 3. We'll try AD, weight of DB. No AD. That's infinity right now, right? AD is infinity. No good. We'll try AE. That gives us negative 4. The weight of E to B does not exist. That's infinity. So do we do any better? You go all through everything, and you get 3. All right. I'm going to fill in a few more here, and then I'm going to do something together with you. I don't want to make it too tedious, but I don't want you to miss an important idea either. This is D2. This is D3. And now, let's consider this spot. Spot C. Spot C and A on top. Okay? Let's consider just that one and figure out what we're going to look at in order to do this. Yeah, Joe.
Is there an if then in that statement right there?
In this?
Yeah, where you're taking the lowest value.
You're going to find the minimum of this. So you're going to need an if then. You're going to need a temporary value. Absolutely.
Okay.
Yeah.
Shai, do you maybe want it the other way around? Because C can't get to A. AC would be more interesting, I think.
Yeah, I meant AC.
Yeah.
So you can get to A in 3 steps.
How?
C to B to D, D to A.
Oh, it's okay. Good. So I'll be able to use it. Does it end up doing it in 7?
Yeah.
Yeah, good.
A
12.
to C is
4, 7, minus 4 gets 7. That's good. That's what I want. C to A.
Well, E to A doesn't work.
That's no good, but 4, B to D.
No. 4, 7. Oh.
C, B, D, D, A.
4, 1, 2, 7. Good. That's what I want. I can do it. All right. I know this is what I want, and we'll see how it works. How do we figure out the best way of going from C to A using 3 edges? It will depend on the best way of going from various other pairs using 2 edges and the original weight. Right? So it's going to depend on these 2. Let's be very, very specific now and circle the values of what this depends on. So the first one is going to be C, A, and A, and AA. Right? M is going to vary from A through E. X is equal to C. Y is equal to A. And M is going to vary A, B, C, D, E. Let's circle all the pairs that we care about. So we get CA. That's, where is that? That's in the D thing. CA is here, right? And that relates with the weight of AA. The weight of AA is? No, on here.
I'm sorry, the weight is there, yes. Right.
So those two match up. You add them up, you get infinity. That's not small. Do the next one. CB and BA. Where does that look? CB, right? And BA.
So you're adding back the third row to the first column.
Third row to the first column. Let's keep going. XCC to CA. All of these are big so far, right? They're all infinities. And then
5 to 2 is 7.
CD, DA. That's where we find the answer. In two edges, we can get from C to D in 5. With one extra edge, we can get from D to A in 2. That's how we get the 5 and the 2 adding up. That's where that 7 is going to come from later. We have to do one more case to make sure we don't get better than 7. We have to check the best way of getting from C to E, and then if there's an edge from E to A, but there isn't. So we take the minimum of the sums of all these, and it ends up being 7. Everyone see that? This is very important to see both these up there, the W and the previous D and the new D. Now, what does it remind you of? Anything? Right. It should remind you of matrix multiplication. You got the first column, the third row, and that fills in this slot. And they all work the same way. This whole loop structure is just matrix multiplication. Except that, what are the substitutions here? What we used to call multiplication is now addition. Right? 0 plus infinity, not 0 times infinity. What we used to call addition is now min. Right? And otherwise, it's all the same. There's a whole mathematical theory about this kind of computation that mimics matrix multiplication, where you have a whole set of operators that take the place of the normal multiplication and addition, but still follow this structure. And there are theorems about everything that follows that kind of structure. And it's a little glimpse into what mathematicians think about. But as far as what you should be concerned about is just notice this connection computationally. This is something you should be familiar with. Once you see it, you can fill in any square in here. If I wanted to go over here, what would I be looking at? I'd be looking at second column, second row. It would be this one and this one, simultaneously going down as we go. This looking at pairs of subproblems is very common in dynamic programming. And setting up your two-dimensional array and your loops to pair them up properly is sometimes a little tricky. Here it happens to mimic matrix multiplication, so you can do it. And I'm finished with this example unless there are more questions, but I do want to go back and explain how we do this faster. And that'll be a separate issue, so you can compartmentalize it. If you understood everything so far, fine. The improvement is not related to understanding the basic idea. Are there questions so far?
You can do matrix math in n cubed, right?
Right.
Does that tell you can do this in n cubed?
Well, when we do this n cubed process, all we do is get from D2 to D3. And we got to do that again and again and again until we get all the way up to dn minus 1. So you're right. It takes n cubed, and we have to do it n times. And that's why we have n to the 4th. By the way, there's a really clever algorithm in the mathematical algorithm arena called Strawson's algorithm. And he gets the n cubed for matrix multiplication down to n to the 2.81. And that's been improved over the years. N to the 3 something might be the world record today. So in fact, you can do better than n to the 4th based on those improvements for matrix multiplication. And you should be aware of that because the gory details of the mathematics is what really makes this algorithm work faster. And there's a lot of discussion about that algorithm. We can do an advanced recitation on it, but we won't talk about it because it's pretty complex. Questions so far? Good? All right, I'm going to leave this up, and I'm going to kill this. And I want to talk about this improvement. And in order to talk about this improvement and let your brains rest for a minute, let's do this little game. It's not really a game. We're going to pretend we're in Egypt, 1800 BCE. I'm going to let what I was thinking go and talk about how they did multiplication. There were no algorithms in Egypt for doing multiplication the way we do it. There was no positional number system. There was no base 10. They did things symbolically. If you wanted to write the number 42, you had 4 things. I forget exactly how they looked, but 4 things that look like this and 2 things that look like that. That's 42. Right? And if you wanted to... Not exactly, because, well...
Just coincidentally, they happen to...
If I put 4 arrowheads and 2 single things in a hat and mixed them up, you'd still know it was 42. If I took the digit 4 and 2 and put them in a hat and mixed them up, you wouldn't know if it's 42 or 24. So hence, positional systems really rely on the position, and they have different symbols for everything. So
For everything. Right?
yeah, they got something for 100. Well, they use base 10, but they have something for 100 and 1,000. There's a cool line in the Bible that basically says, this is Joseph going, it's the Old Testament story, he goes down, he's Pharaoh's happy little helper, and he's taking care of the famine. And there's a line that says he was real clever and he spent 7 years collecting lots of stuff so that when they had the 7 years of famine, everybody would have plenty of food. And then there's a line in the Bible, a little mathematical line, that says there was so much grain that there was too many grains to count. You know, a nice way of saying that there was a lot. But in Egypt, that made a lot of sense. Because the minute the number of things you had got past the symbol they had for the biggest thing, you just have to keep writing that symbol over and over and over again. And at some point, you don't bother counting it, because it's too much of a pain in the butt. So it actually makes sense culturally that numbers that were very, very large, you didn't count them. They were just beyond what we cared about. When you have a positional system, you can work with anything. Adding an extra digit doesn't really matter. So it was probably just a nice metaphorical literary device, but I like to read a little into it. Here's how Egypt did mathematics. They did addition in a normal way. You would take these symbols and you would group them together. And if you got too many of one symbol, you would take them away and make a new one of the next symbol, kind of the way we do grouping. But they had no way to do multiplication because they didn't have this positional system. So they would do it by repeated addition. But if you wanted to do 16 times 42, and you wanted to add 16 to itself 42 times, that's a lot of addition. So, if imagine you're a little kid in 2000 BC, and you don't want to do 16 plus 16 42 times. It's a pain in the neck. So, of course, they had a more clever way to do it. Instead of adding 16 to itself 42 times, they would double 16. They'd add it to itself once. And then they would double that. So that's just the second addition. And then they would get 4 times 16. And then they double that. And they get 8 times 16. And they double that. And they double that. And now they'd stop because they knew that they're already going to get over 42 times 16. And now they look. They go, okay, I got 32 times 16 here. That gives me 40 times 16. And I add that, and that gives me 42 times 16. So how many additions altogether this way? 1, 2, 3, 4, 5, 6, 7. So 7 additions instead of the 42 additions. That's a really, it's 4,000 years old, that idea. It's called repeated doubling.
But they would have done it in the 4 additions if they did it 42 times 16.
Yeah, and they probably would have done that, but I would have not been able to explain the idea as well. Right, they probably would have done it the other way. But regardless, they didn't leave a lot of explanations about why they did things, just a lot of lists of how they did things. So it's all speculation. It's ancient history. Nobody knows really what was going on. In any case, this improvement that Zvi hinted at is an improvement that's based completely on this idea. So it's not a new idea. Here's where it comes from. When we do this calculation of the next d, it's based on the old d and the weight array. Right? So dk plus 1 depends on dk, and d1. And when we do it again, dk plus 2 depends on dk plus 1 and d1. It's like, if you wanted to get up to dn minus 1, doing repeated calculations over and over again, n minus 1 times. What's a faster way of getting to d64 outside of doing d1 times d1 gives me d2? d2 times d1 gives me d3. d3 times d1 gives me d4. Duh! So, right, do d32 plus d32. Do d16 and d16. Do d8, d8, d4, d4. Do it in that repeated doubling way. It saves you lots of calculation. How does that correspond to our idea here? It makes a lot of sense. It completely corresponds. So let's think about it. If you want to find the best path from x to y that uses k edges, why don't we find the best path from x to m that uses half that many edges, and then connect it with the best path, not the best weight, but the best path from m to y that uses half that many edges. This is just the old, why split a problem into 1 and n minus 1 when you can split a problem into n over 2 and n over 2? It's that same recurring computer science idea, and the Egyptians understood it, and we should have understood it here too. But if I had started it that way, maybe this whole thing would have completely, I don't know. I'm not sure if it's good to start with this or just to go to the k over 2 over k over 2. But once you've seen the d and the d1, I think you can really appreciate how much faster it's going to go if we replace this w and this d with dk over 2 and dk over 2. So how do you do this in practice? In practice, you start out this being d and d. And then you copy it back again. So the next time, these are both d2. And then you do d2 and d2. So the next one you copy back is d4. Then you do d8 and d8. The next one you copy back is d16. Then you do d16 and d16. The next one you copy back is d32. So say I have 38 nodes in my graph. I got to do it more, right? So I do d32 and d32, and I get d64. And then I stop. You don't have to get exactly d38 like the Egyptians had to, because here, once you get past d38, it's all the same, right? So just do as many as you need to get over the one you're looking for. It only costs you one extra iteration. So if you're looking for 38, go all the way until you get to the power of 2 that's the smallest over 38. So what is that number? That number is the logarithm base 2 of n plus 1, or the ceiling of the log base 2 of n. So instead of getting n cubed times n iterations, we now get n cubed times log n iterations. Does everybody get that improvement? That's a big improvement. I mean, it really makes a difference in the speed. And it's really, really no reason to ever do it this way. Now let me stop. Are there questions about that?
This means we can get rid of the original weight array, so we have no, we also lose having to keep that around.
Right. You don't need the original weight array, and you only need to keep the iterative d array. Absolutely. I mean, it's your input, so you probably wouldn't get rid of it. You might need it for something else. Yeah, whatever. You don't need it in this algorithm. Absolutely true. All right, questions about this? Okay.
When you say that you don't have to stop early, you can just double up to 64 or whatever.
Yes.
You're looking for 38.
Right. That adds one more step to your whole process.
Right. And that's because of the thing where once you reach n minus 1, they're not increasing anymore?
Exactly. Once you reach n minus 1 iterations, your d stays the same. You can do it as many times more as you want, but it'll never change.
So that's only the case when you've reached the total number of nodes for a full shortest path. If it's like a partial.
If you want a full shortest path, double back and forth, all you need to go ahead and do is get past the number of nodes in your number of nodes minus 1.
Having passed it, you can still you can find a shorter path by adding length, because you can.
You could, right? I mean, you could, if you were going to 38, for example, when you got to 32, you could stop and then do 6 iterations using the w to get up to 38, but you wouldn't do that. You're better off jumping right over to 64, right? I know you're tired, and I'm not going to start a new topic, but I want to finish a little bit more on this, and then I'll let you go. Just a teeny bit more, just a teeny bit. I'm going to write a variation of this loop over here. It looks like this. Everything stays the same, except now, instead of this k going from 2 to n minus 1, the k is going to go from 1 to log n. Okay? You have to do it much fewer times. Everything looks exactly the same. Inside here, where the m is, for all these m, you have dxm plus dmy. So instead of using a w, you use a d, and instead of doing it n minus 1 times, you do it log n times. Otherwise, everything's the same. Okay. There's only one more thing I want to add to this picture to complete it, and then we'll do the better version of this tomorrow, and we'll do another dynamic programming example tomorrow. We'll do the matrix multiplication one. The thing that's left over is, where do I store the pointers? It's a minor detail, but it's part of every dynamic programming to have the following feature. You calculate the minimum or the maximum of something, and then it corresponds to a path or an ordering or a set of things. And you've gotten the minimum or maximum cost, but you want to know what set or ordering actually corresponds to that. What path will be this path that takes 20 to go from here to here? Picking out the actual collection of things that give you that minimum or maximum cost is often important. And in every case, it is a minor thing to do that. There is always a place in the dynamic programming structure to store information as you go, so that later on when you're done, you'll be able to retrieve that information. In this case, it's in a form that you've seen before. It's the shortest path tree form. We're going to have a two-dimensional array, P of ij, that stores the shortest path trees. And if you want to get the path, you go to the particular j you want, follow the pointers back, and print them out as you go. So you've seen a way to do it before. The only question is, how do we construct it? When we do the dynamic programming algorithms that are coming up, we're going to have to think of a way to store the information, and then when we're all done, a way to retrieve it. Very often, the way to retrieve it is recursive, not dynamic programming. The way to retrieve the shortest path is to start at j and have the pointer call the shortest path from its parent to I, and have the recursion call the shortest path from its parent to I. So retrieving the information about the best cost is almost always recursive. Storing it is stored on the way down in the dynamic programming. It's going to happen here. It's going to happen inside this loop and inside this loop. And it's going to be different in this case and this case. So let's think about it and think about what it means. And it's one line, so if I write it down, it's going to seem like it's easy, but it's not so easy at first glance. You're liable to think of the wrong thing. So let's think about it really, really carefully. Let's say we figure out that a particular one of these values, m, is the minimum one. We know that's the best one. Okay? We know that going from x to d, and then adding the edge d to y, is the best way of going from x to y. Then what parent should change in our parent tree structure? It's the parent of y, right, in the shortest path tree that was rooted at x. And what should it change to? Pxy is now going to change. The parent of y, the way to get to y, in the shortest path tree that's rooted at x, no longer comes from where it used to come from. Now it comes from another place. Where does it come from? From m. How do we know that? Because the last thing we did was take this edge from m to y. So the parent becomes m, where m is the minimum of all these. Where m is the one that really got us the minimum. So I'll write the best m from that loop. You have to keep track of it and then do the appropriate copying over. That's straightforward. It's different here. Why is it different? Because this m represents a node that has a long path over to the y. The parent of the y isn't going to be an m, because m might not even be connected to y. It's the same beginning. It's the same pxy. We have to change the parent of y in the shortest path tree that is rooted at x. But it's not going to be equal to m. No. What's it equal? It's equal to... All right, I'll put money down that Chris can get it if he stares at it for 30 more seconds. So tough luck. You can't tell me. All right, you want to tell me? You figured it out?
Well, you'll need to y's parent rooted in x will be the parent of y rooted in m, and m's parent rooted in x will still be x. So it'll be
All right, it's fun to see Chris's mind work as he figures it out. He's exactly right. So let me summarize what he just said without the final brain check. Pxy is the parent of y in the shortest path tree rooted at x. We want to figure out where we should come from when heading to y. All we've learned now is that in going from x to y, we have to go through m. But we've got a shortest path tree rooted at m. That shortest path tree tells me that if you're heading from m to y, I'll tell you the parent of y. That's the parent of y now in the shortest path tree from x. Whatever y used to come from, it no longer comes from there anymore. It comes from the same place that you would come from if you started in m. But we've stored that. So instead of m, it equals pm
So do we actually have
y.
the shortest path forest at any time in this? Like one for every...
That's m.
A shortest path rooted in every node?
You have a shortest path rooted in every single node, right. You have a big forest, they never connect. You have n separate shortest path trees. Very good point. This is so easy to write down that it really belies the complexity behind it. Make sure you understand this idea, and if you don't ask me, I can explain it when you're not tired and we don't have just 2 minutes before you have to run to lunch. But the idea is straightforward, and if you grasp it, it won't seem, woo from the blue. But concentrate on the difference between this line and this line. And concentrate hard on it, because the book in this section, they do talk about this n fourth and n to the cubed log n. They completely ignore the parent discussion in this section. They only talk about it in the improved Floyd-Warshall section. They act almost as though you can't do the parent in this example. And that's not true. It's easy to do it. You just put it in here and you put it in here. And this is exactly the kind of stuff you can do and should do in every dynamic programming algorithm. And it always is challenging for beginners at the beginning to figure out where you should put this information and then later on how you retrieve it back. So practice it. And it will be hard at the beginning, and I will help you. So it will become easier. All right. Let's call it a day. A day.